Advantage of this high compression, the higher the compression ratio, the higher the expansion ratio, which means when I take that air and put it into a small area and then I light it on fire, when that fuel burns, it expands. And the more I compress it, the more it's going to expand, the more energy I'm going to get out of every gallon of fuel that I put in there. As it expands, it's going to cool because it's exposed to that cooling system, those fins. So as it expands, the higher the expansion ratio, the more energy actually moves the piston rather than just going into my cooling system. That's why if you look at a diesel engine when it's running under a load and you feel the heat coming off the exhaust pipe, then take a gas engine under the same load and fill it, a gas one will be a tremendous amount of heat coming off because it's all going out the tailpipe, comes out the radiator. In a diesel engine, it's gone into expanding the piston, not out the fins, out the tailpipe, and out the radiator. So they tend to run cooler. It mixes better. The tighter you compress that air, the more the molecules are going to move around. The more they move around, the better they mix the fuel. The more activity means more efficient burn. The higher compression ratio equals a small combustion space. There's less heat lost out the walls and the fins. More spent gases are actually pushed out the exhaust pipe, which means more air is drawn in. I'm going to have a more efficient burn. Once I'm in there, more fresh air means better combustion. Limitations. What limits a gas engine? The limit on compression ratio and expansion ratio has to do with the mixture, and that's the octane level. When you go to the gas pump and you look at the 3 different octanes, that's the flash point. And that's going to be our limit on how much compression we can get out of an engine. It's determined by the octane level, and that's why we stop at 14 or 160 pounds of compression. On a diesel engine, there's a point in which there's no more room for expansion. There's no more space left. And so when I start my fire and it doubles in space and I have like a pinhead of a space left, there's not much change. And if I double a pinhead again, I still don't have much change. And so there's a point in which if you graphed it, the graph would go up, 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 all of a sudden it goes wham and it drops off. And you just don't get any more out of that fuel. And so there's a point. And that's 25 to 1 or 24, whatever the number was I gave you up there. And so there's a certain point you just can't go past that. The pressure, you try to compress that much air, and with that much, 500 pounds of compression takes a lot of energy to create 500 pounds of compression. And so the pressure on your bearings, you have to have a bigger crankshaft, bigger bearings. It just takes more to hold that air in there. The seals, which is your rings, takes thicker, bigger, heavier rings. The friction loss is too extreme. It gets to a point where you have so much bulk in that engine that the friction loss outweighs what's actually your usefulness. Heavier starting takes such a big starter and so many batteries that the weight, and in our industry, weight is everything. We got these greens mowers and stuff. We don't want the weight, and the weight just outweighs the benefit. And then the higher compression ratio means it's going to take more fuel, and pretty soon you get to a point where all the advantages become all disadvantages and you just kind of run out.